Hello everyone, I'm Ali Reza from University of Leibniz Hannover, and I'm privileged to present a work from our paper Phonics at LLMs for Ontology 2025, Task A, Ontology Learning with Large Language Model Reasoning. This article was prepared in collaboration with Massa from the University of Tabriz. To begin, let's establish the context. We are generating data at an unprecedented rate, but much of it unstructured. The vision of the semantic web is to address this by making web content understandable not just to humans, but to machines as well. The core building blocks of this vision are ontologies. An ontology is a formal model that represents knowledge by defining the concepts, categories, and relationships within a specific domain. Think of it as a dictionary for computers that provide context. However, there's a significant bottleneck. Manually creating these ontologies is an extremely complex, expensive, and time-consuming process. This is the problem that ontology learning aims to solve. The automatic or semi-automatic construction of ontologies from unstructured text. And this is where large language models enter the picture. The rise of generative AI has revolutionized our ability to process and understand natural language, offering a powerful new tool for automating ontology construction. Our work was part of the LLMs for Ontology 2025 challenge. We are specifically focused on Task A, which is a foundational to the ontology learning pipeline. Task A itself is divided into two distinct subtasks. Subtask A, term extraction, and subtask A2, type extraction. For term extraction, the first step is given a set of documents from a domain. The goal is to identify and extract all the relevant domain-specific terms that will form the basics of ontology. And for subtask A2, type extraction, then using the same document, the model must then identify the types or categories for those extracted terms. These types will eventually become the classes in the ontology. This provides a clear two-step process. First, find the things, then figure out what kind of things they are. Now I will a little bit talk about related work. It's important to place our work in the context of existing research. The field of LLMs for ontology engineering is rapidly evolving. Some researchers, like Schmitz et al., advocate for modular ontology design, showing that LLMs perform better when tasks are broken down. Others, like Lipolis et al., have explored prompt-based methods for generating ontologies from question finding that LLMs can outperform novice 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 humans, but still require manual refinement. Our work our work differs from approaches like OLLM by Liu et al., which fine-tunes an LLM to build taxonomic backbones. And studies like Baker or Baker et al. Have evaluated LLMs in real-world scenario, nothing strengths in identifying classes, but weakness in modeling relationship. Our paper contributes to this landscape by specifically evaluating a prompt engineering only approach using chain of thought, which doesn't require costly fine-tuning. Now I will talk about our methodology and prompt engineering. Given the task, we had to decide on a methodology. Instead of fine-tuning, we focused on prompt engineering. Our central hypothesis was that we could guide powerful pre-trained LLMs to perform this complex task using carefully crafted instructions. We observed that LLMs can sometimes struggle with complex reasoning. To overcome this, we adopted a chain of thought fuchsia prompting strategy. Why we decided chain of thought? COT prompting encouraged the model to generate intermediate reasoning step before giving a final answer. This is perfect for our task. Instead of just splitting out a list of terms, the model is forced to think about to process. First, I will read the text, then I will identify technical nouns, then I will filter out generic words. This leads of more structured and interpretable reasons. And why we decide few-shot? We combined COT with few-shot example by providing 1-2 examples of the task being solved. We give the model a clear template to follow, which improves both accuracy and consistency. And this slide, it can be seen here, the snapshot of our actual prompt for subtask A1. We didn't just ask extract the terms, we provided explicit step-by-step instruction. Understand and the topic, read the title and text to identify the domain. Then identify technical terms, look for specific nouns and nouns phrase, and filter out generic terms, exclude common words, function words and verbs, then rank by relevance, sort the terms and select the most important ones, then present only the terms, list only the final terms, and he then provided a concrete example showing this exact reasoning process in action, followed by the placeholder for the new text. This structure guides the model to replicate our desired reasoning pattern. For this challenge, We selected three state-of-the-art instruction-tuned LLMs to test our prompts. At first, Queen 2.5 72 billion instruct, and Mistral Small 24 billion instruct, and Llama 3.3 70 billion instruct. We evaluated this model across the three official datasets provided by the challenge, each representing a distinct domain: ecology, focus on concepts and terminology in the ecology domain; scholarly, dealt with academic publishing and scholarly communication; and engineering, a technical dataset derived from engineering process and terminologies. Performance was measured using the official metrics: precision, recall, and macro F1 score. Now for our result. Let's look at term extraction subtask A1. The results were fascinatingly domain dependent. In the scholarly domain, Queen 2.5 achieved the highest micro F1 score at 0.3950. However, Llama 3.3 had a much higher recall with 0.5312, meaning it was excellent at finding many potential terms, even if its precision was lower. In the engineering domain, the results were different. Llama 3.3 had the best F1 score in the F1 score, but Queen 2.5 had the highest precision by far at 0.4893, indicating it was very selective and accurate, though it missed many terms. The key takeaway for A1 is that our COT approach shows promise, especially in domains with well-defined terminology like scholarly, but it struggles more with the ambiguity and technical depth of engineering. Now we're moving to subtask A2, type extraction. Game performance was highly varied. In the ecology dataset, Queen 2.5 was the top performer with the highest F1 score, 0.4309, and recall 0.5442. In the scholarly domain, Mistral Small took the lead with the highest F1 score and precision. Meanwhile, Llama 3.3 dominated recall and recall at 0.6, showing it could correctly identify the types for a wide range of terms. The engineering domain was once again the most challenging for all models. Queen 2.5 achieved the highest F1 score, but it was a low 0.1846, Interestingly, Llama 3.3 is still managed a hierarchical of 0.5. This shows that the conceptual complexity of a domain is a major factor. Our prompting strategy was effective in domains like ecology and scholarly, but, uh, but assigning types in technical fields like engineering remains a um, hardly, significant hurdle. Now I will talk about our conclusion and summary points and our summary points. In conclusion, our work explored the use of LLMs with chain of thought and few-shot prompting for the foundational tasks of ontology learning. Our finding our findings demonstrate three key points. Prompting strategy matters. Combining COT reasoning with few-shot example can effectively support terms and type extraction across different domains. The next one is domain. Domain is king. Performance is not uniform. The model showed particular strength in domains with clearer, well-defined conceptual structures, while the complexity of the engineering domain posed a significant challenge. And the next one, potential without fine-tuning. Most importantly, this result highlight the potential of using advanced prompt engineering as a viable strategy for ontology learning without resorting to resource-intensive, task-specific fine-tuning. At the end, we would like to thank the organizers of the LLMs4OL 2025 challenge for providing the datasets and evaluation framework that made